Hello, so let's get going with one of the DAA questions I did. This was the second question. Question 4, we have part A. Consider a graph with vertices v is equal to a, b, c, d, and edges a, b, a, c, a, d, b, c, so on and so forth. So in part 1, we're asked for every vertex, give the discovery time and finishing time and a depth first search starting from A. Whenever there's a choice of vertices, pick the one that comes first in alphabetical order. Okay, so this is pretty straightforward. We just kind of write out what the matrix is, right? I kind of just mapped it out using a matrix, so that kind of makes it a lot easier for me to see visually. And then we start at A, right? And then run DFS program. So we're just gonna keep track of the D, which is like the kind of discovery time, and the F is the finishing time. Starting off with A, we keep 1, and then A can lead to B, so B's discovery time is 2. And then I see that it can lead to C, so C's discovery time is 3. And then C leads to D, so D's discovery time is 4. And then we see that D doesn't lead to anything, so we're done with D, so we're gonna backtrack. So D is done in 5. And then we're backtracking to C, right? There's no more things to do with C. So we're gonna be 6, and then we go back one more step. D is already visited, so we don't need to do anything. So then B is 7, and then we finally go back to A, and then A is 8. So that's basically the time for that. And then in the second part, we have suppose that we perform a DFS starting from another vertex. Perform a depth first search starting from C and give the discovery and finishing times. Whenever there's a choice, also do alphabetical and give the discovery and finishing times. Okay, so this part it was if we start at C, we realize we erased this part, so it's not. I'll do it with color B. Blue. So like if we're starting off at C, right? C is discovery time is 1, and then we see that C leads to D, so then D's discovery time is 2. And then we see that D is finished because it doesn't lead to anywhere. So D's finish time is 3, and then we go back to C and C is finished. So C's discovery finish time is 4. And then the thing that I kind of missed at the time when I was just done, I was just too carried away and just say I'm done. But re in reality, because DFS goes through the whole list, right? Next, they'll go to A. A would start at 5, and then we would start the process over, right? 5, and then A goes to B, B is 6, and then B is finished because C and D are already done. So B finishes at 7, and then A finishes at 8. So that would be the discovery and finishing times. Yeah, I kind of forgot. Like the minute I was done with D and C and D, I was like, oh yeah, I'm done. But yeah, it's not finished there. Mm, for the next part, for part B, we're asked, this question is about DAG of G equals VE. Describe the topological sort algo and then prove its correctness. So for this, basically, this is sort of bookwork. So topological sort for DAG kind of produces a ordering of vertices such that for every edge UV, vertex U comes before the vertex V. Um, in this ordering, we can do topological sort by first calling DFS to get the finishing times for all vertices. And then we just take the ordering and output it by decreasing finishing times. So that way we can make sure that there's no kind of out of order. And why is that true? Yes, this one is not the best. Like basically this is just writing out what I would say, but I think there is a better kind of explanation. Yeah, I'll go for both. It's just kind of just talk about it, but it's the same idea. But this one's not written out formally enough. Here what I said was basically for directed edge inside this, for UV inside the edges, FU is greater than FV because we just want to see the finishing times, right? So when we call DFS, what we're going to do is we're going to first have U. And because we already found U, but we haven't ex finished exploring it, so it's gray technically. And then next, we just break it down into 3 scenarios, whether V is white, gray, or black. If V is white, so basically it has not been explored yet, so then it'll become a descendant of U. So by parenthesis theorem, we have du is smaller than dv smaller than FV is smaller than FU. So that's the idea. So it's actually legit. In the other scenario, when V is black, it is already visited and finished. So FV is smaller than FU. And then the case that V is gray, it's not possible because we would see that it would technically mean that U is a descendant of V, which means that it would have been a back edge. But DAG by definition cannot have cycles, so this case of the gray edge is not possible. So hence in both cases we see that for the both black and white, FU is greater than FV, so it will be sorted. So that proves the correctness of topological sort. A more formal way of kind of proving this would be sort of breaking it down into a proof by contradiction sort of thing, where what I do is for edge of UV and edge in the E thing, I want to prove that FU is greater than FV, right? So by parenthesis theorem, I assume the contrary, that FU is smaller than FV. And that in this scenario, I would have two cases, right? Either if U is V's descendant, then it would have followed this. So if UV is inside this edge, then descendant points to the ancestor, which forms a cycle, which means that's not possible, right? In the other scenario, there is no ancestral relationship. So then it would look something like this. So it basically means that the vertices are kind of destroyed. So edge cannot exist. So then we can't have that relationship, right? So for both scenarios, you have FU um, smaller than FV doesn't hold. So the only scenario that it could hold is FU is greater than FV. For me, I feel like the first one is more intuitive in terms of just like splitting up into those three cases. I think it would have been better written out, but proof by contradiction definitely works and is more formal, say. And then part C, we're asked, let G be a graph with n vertices labeled from 1 to n with adjacency matrix aij equals 1 if I smaller than j and 0 otherwise. Suppose that a depth first search is performed from vertex V and that whenever there's a choice of vertices, the vertex comes first in lexicographic order is picked first. Let DI and FI be the discovery time and finishing times of the ith vertex, respectively. Show that for every I, one has the bound 2n minus 2i, the DI is in between this 2n minus I plus 1. So actually, the idea is that we first find what it is, like the value exactly, and then show that it's within this bound. So yeah, this is a condition that we have. We're just gonna, because we see that in the end, we see the bounds are something in minus I, then we know that, okay, we're probably gonna have to work backwards to have this in minus I. If we work forwards, and we're not gonna get that, right? So let's say that we start from n, right? If we start at n, the discovery time of that would be 1. The finishing time of this would be 2 because there's no outgoing edges for n, right? Because in this vertex, because aij is equal to 1 if I is smaller than j. So then the next one would be for n minus 1, it would be discovery time would be 3, and then the next one would be 4. Because if it was if there was anything else, then it would have it would have not worked because there's no more outgoing edges, and the only outgoing edge is to the next part, which was n. But n is already visited, so hence it's not possible. So then that's why we have the discovery times 3 and the next one's 4. And then for everything else, it would have been similar, but same story because everything else that leads to it is the later ones. And the later ones are already processed. So every time it's just going to be 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth for each one. So up to our ith index, what we have would be the discovery time would be 2 times n minus 1, n minus I plus 1. That would be the case, right? Because it's just 1, 3, 5, 7, 9, so on and so forth. So then this would be our discovery time. And we just see that, okay, yeah, it fits within this boundary that we have because, okay, yeah, 2n minus 2i, and then we have plus 1, so that's bigger than that. And the I is from 1 to n, so hence the right bound is also true. So yeah, so that's how we show that it's true, because we just found it definitively and show that it's within this bound. And then for part D, we have, I think this is like the more interesting question from this problem, is that we have an investor who's interested in investing in a set of companies. However, investing in a certain company may be incompatible with investing in another company. Let this graph be the undirected graph where vertices represent companies and the edges represent the incompatibilities. So basically, you can't invest in two things that are connected. For every vertex v in V, let PV be a positive integer representing the expected profit when investing on V. The goal is to find the subset inside this that maximizes the total profit under the condition that no two vertices in S are adjacent. In part I, we're going to assume that G is acyclic. Design an algo that finds the set S with maximum profit and prove that the algo has running time this. Okay, so for DI, what I would do is something like this. This is the code. I don't think it's that clear. I think, yeah. Yeah, I'm gonna go with that because it's the only thing I have. It's not written out very clearly. But essentially what the idea is that we first realize, okay, if we have an undirected acyclic graph, that it must have meant that it's either a tree or a forest of trees, right? So there's also the idea that this problem it's kind of hard to use a greedy approach, right? If we're doing a greedy approach, we're not sure we're going to get the best scenario. So this means that we probably have to do a dynamic approach on the trees. So yeah, so we're going to be doing dynamic programming on trees. So that would be our approach to get it to the time complexity. And additionally, to do dynamic programming on the trees, it means that we have to go through the trees, right? Breadth first search won't work because it's kind of hard to keep track of the previous cases. So then the only way we can kind of work around this is post-order DFS, because we need the children to kind of determine what the parent should be. So yeah, that's why we use post-order DFS on trees for this question. And we're just going to define kind of some of the arrays that we're going to be working with. So we're going to let P in V kind of be the array of that stores the maximum profit for subtree rooted at V initialized to the thing itself. And then we're going to initialize P out V to be assuming one this is excluded from that at the subtree. So basically the idea is, okay, if I have a tree, something like this, um, then I would have, okay, this is my parent, right? My parent would be either included or excluded. So I have two cases, whether it's in or out. And then in the case that it's in, I would have to take the out of the children, right? The sum of the out of the best cases of the children. And if it was out, then I would have the flexibility of choosing either in or out of the children and taking the maximum sum of that. So that's the idea. And I would just find the maximum of that and keep it in the in and then keep it in the out. And I just recursively go up the tree and then update the values. And then I have a list of, an array that's called visited. Basically, it's all initialized to false, basically tracking the DFS. And then children basically tracks the parent-child relationship. So whenever I go to a vertex and I see that it has a parent or children, I would add that relationship in. And then specifically what the algo would look like would be, I first go through each of the vertex, right? And I'm going to be calling, if it's not visited yet, then I'm going to call the DFS algo on it. So that I make sure I go through all the vertices because it might be a forest rather than a single tree, right? Not all of it might be connected. So that's why I kind of have to go through this for loop to make sure that I go through all the vertices. Next, in my actual DFS algo, when I input the vertice at the root, then I would just mark it as first visited is true, just to make sure that I keep track. Next, I just do a for loop through all the connected neighbors of all the connected neighbors. I'm going to call W of V. So if the neighbor is not visited yet, then I'm going to add it to the children, and I'm going to call DFS on it, right? Going to iterate down and find what the children are. And then for the children, after getting that back, then I would just do, if it was the two cases, I would just break it down into whether the parent was in or out. If the parent was in, then I could take the parent value, right? I can include the parent value of whatever is at here, and then plus whatever the out of the children are, right? Yeah, this is the out of the children. And if it's not the case, then like I choose to exclude it, then in my excluded list, I would just have whatever was excluded plus the maximum of the in and out of the children. If the children was the maximum was in, then I could just take the in. If it was out, I could take the out. So I'll just get the maximum of that. The in doesn't actually, if I chose the parent to be in, then my child can't be in, right? But if it's out, I can do both in and out. It gives me more flexibility. So that's how my recursive function works. And then this kind of function of running this DFS algo kind of finds me the maximum profit of maximum profit of the thing, right? But the problem doesn't necessarily stop there. It asks me to find the actual subset. So what that means is I have to go through the algo again to kind of reconstruct what my set is. But now with that, I already know what the maximum profit is, right? So I'm just going to go through all the roots of the tree in the earlier part, and I'm going to call a function that I'm going to say is called construct v false. So what that construct is I take the vertex and then I take parent included, a Boolean value. So if the parent was included, then I'm going to set this to be false. Otherwise, in the case that my in was greater than out, then I'm gonna make it true. Otherwise, in the case that out is greater than in, then I'm going to make it false. So basically, in other words, I'm going to make it false if the parent was already included, so I can't include the child, right? Or also in the case that like basically the out is actually the maximum of that is bigger than the in, then it makes sense that I just don't include it. So in those two cases, it would be false. Otherwise, it would be true. So then for each of the child in the children, I would just call construct child and then include this. And then this means that I go down through the tree and I make sure that each one is the maximum output, right? And that I just return S, which would be the set that I'm interested in. So for the complexity of this algo, initialization of all the arrays, right? That would be O of V, because each one would be taking up some kind of V, right? Because that's the size of the array, several to that. And then in this first part where I'm trying to call the DFS part, this bottom up approach, I would have to go through the vertices and the edges, which would be OV plus E. And then the loops that I go through, each of the operations inside would just be 1. So hence it would just be OV plus E. And then the top-down approach, I would have to go through each vertex and then hence it would be OV. So then my algo in total would be OV plus E, which would be what I need. Okay, yeah, that was a bit difficult, I'd say. This question was definitely quite hard. For part two, we have assume that the graph G is acyclic and that the profit function PV is constant. Design a greedy algo that finds and prove that it finds the optimal set S. Okay, so for part two, it's much, much simpler because we have the PV function is constant, right? So the minute we see that the PV is constant. Okay, this one was not really written out very well because it's not very clear. But I just kind of go through here. So the idea is that, okay, I'm gonna go through first here because it's more written out and then go through the actual more formal proof. The idea is that if PV is constant across all the nodes, then it doesn't matter to me which one I pick. My greedy approach is that I'm gonna just find the maximum number of vertices to maximize my cost, right? So then the idea behind this is that I'm going to try to find the leaf node. And then leaf node by definition is the ones that have exactly 0 or 1 edge connected to something. And I'm going to add V to S and then remove the V and its neighbors and its subsequent like edges. from that graph, and I'm going to repeat this process until the graph is empty. So that this is kind of my greedy algo of what I would do. And then the proof for this is this idea. I'm going to first walk through the idea and then the actual kind of code, like kind of like the actual kind of more formal proof. So we have let S be the optimal set. If there was a leaf and vertex V that share edge, U and V cannot be both in S, right? So the maximum, I feel like, yeah, you know what? I don't need to go through this. I think it's just better if I go through the proof this way. So it's better to structure it to prove it into by proving two lemmas. The first lemma is that for any leaf, there exists a optimal set S which contains V. So how I'm going to prove this lemma is that basically I'm going to kind of define a S that is a optimal solution, like the S bar. If the vertex of my leaf was not in S, then the parent node of the thing of my V must be in S, right? Because if it wasn't in S, then the profit would have been less, which would be problematic. And it wouldn't be an optimal solution. Hence, the parent should be in S if that's not the case. Because as a profit function is constant, we can replace this parent by our V to form the set S equals this thing, right? And because we can swap it, the total profit would remain unchanged. So S would be an optimal solution as well. So there could be two existing optimal solutions. So that's why our leaf is always can be included into the optimal set. And the second kind of um, lemma that we need to prove to kind of show that we need the leaf is that after removing V and um, the parent of V, let S1 be the solution of the remaining graph G1. So basically what we're doing is, okay, we have, let's say this was our original graph with our final thing was connected to this one was a parent of V. Let's call this parent of V. And then this was connected to our leaf. So if we were to remove this part, completely cut this off from the graph, then what remains is our graph. We're going to call this graph that remains G1. And then for this graph G1, we're going to say that, okay, S, which is our optimal solution, should be the optimal solution S1 inside this graph combined with this, right? So basically, whatever best solution remains in this graph, not including the parent and then including this leaf, should be the optimal solution. So how I'm going to prove this is basically by contradiction. So I'm going to assume that now that S1 is not optimal. This one is not the optimal solution. Then there must have exist some S1 prime in this combo that is better than S1, right? It yields a better profit. So then I can construct S prime to be S1 union of V. So I can do this one with this one that way because this one's already not included, right? So then this would have meant that S1 prime is bigger than S1 because if we construct P of S prime to be P of S1 plus P of V, right? P of S is equal to P of S1 plus P of V. But then that would have meant that PS prime is bigger than PS. But this kind of contradicts our first assumption that PS was the graph that was the optimal solution. So then if the optimal solution is not the optimal, then we have a contradiction. So hence this is not possible. So hence the leaf must have been S1 must have been the best solution and V should have been a also part of this, right? So that's why we can show that every time removing the leaf would be our kind of greedy optimal approach to solving this problem. Yeah, so overall, I think this kind of question. I think the first part A was definitely a point giver. Part B was also sort of bookwork. Maybe like the proof, I think, is a little difficult, but it's all right. But I think definitely C was doable, and then D is like mainly the hard one. Is kind of the proof of part two, and then just the algo in general, part one.